Hi, folks. We're going to take a look at this identity here from page 240, number 16. So first step is to decide which side we're going to start with. Now, while there is some manipulation I can do with the left-hand side here because of the double angles, it really looks as though the right-hand side provides more opportunities to manipulate. So I'm going to start with the right-hand side here. Okay. And what I have is I have two compound angles. And so I'm not going to think about it. I'm just going to apply the compound angle formulas for sine of a sum and cosine of a difference and just see what happens. So I've got this 2 in front. So I'll use bigger brackets there to separate them. So sine of x plus y is just sine x cos y plus cos x sine y. Or you can think of it as sine of the first, cos of the second, plus cos of the first, sine of the second. And then here, this is multiplying cos of x minus y, so that's cos of the first times cos of the second, plus, so remember when it's sine, it keeps the same sign. When it's cos, it's the opposite, so this is going to be plus sine x sine y. All right. Now, at this point, there's not much I can do with any individual term. So I think my only option is to actually distribute this whole thing out. Okay, so let's make sure we do it very carefully here. So let's multiply these two firsts here. And I notice that they both share a cos y. Okay, so that means I'll have sine x cos x times cos squared y. All right. So let's go to the, outsides. So here I notice that they share a sine x. So I'm going to have plus sine squared x. And then it looks like I'm going to have cos y sine y. And just to keep things in sort of this similar order, let me put the sine first. Okay, which of course I can do because multiplication is commutative. So sine y cos y. So let's now go to these inside terms. So here we've got plus, and I see that the both share cos x, so I'm going to have cos squared x, and then here sine y cos y. Now already I'm seeing something very nice because sine y cos y, these things have a common factor, so I'm liking that. All right, and then plus, let's do the last one here. So they share a sine y, so I'm going to again write this as sine x cos x. And then this is going to give me sine squared y. All right, and this is where I see that, hey, sine x cos x, sine x cos x. We already noticed this sine y cos y, sine y cos y. So I'm going to bring together those with like terms. All right, so 2 times. Don't forget that 2 in front. So I'm going to take these two terms and I'm going to remove the common factor, sine x cos x. All right. And what do we end up with here? Well, I have a cos squared y from that first one plus a sine squared y from the second one. All right, let's do the same thing here. I'm going to remove the common factor of sine y cos y. And what are we left with? Well, we're left with a sine squared x plus a cos squared x. Whoops, forgot the x there. Cos squared x. All right. And here, this is where we notice, hey, sine squared x plus cos squared x, that's just equal to 1. And here, sine squared y plus cos squared y, this is also equal to 1. So let's see what we're left with here. We're left with a sine x cos x, which I'll now distribute the 2. So 2 sine x cos x, which I hope you're seeing looks familiar. And now I'll distribute the 2 to that second term there. So we're left with 2 sine y cos y, and this is where we recognize this as the double angle formula for sine 2x, and this is just the double angle formula for sine again, but this time with y. So this is just equal to sine 2y, and lo and behold, that's exactly my left-hand side, and so the identity is proved. Okay. So this one here didn't have anything fancy in it, but it did certainly have a fair bit of algebra to do. So step number 1 was to identify this right-hand side as being the more complex one. So that means offers more room for manipulation. Okay. I just applied my compound angle formulas and then realized that the only option I really had was to multiply everything out. But luckily it worked out quite nicely because it gave us common factors that we could remove. And then when we remove those common factors, we just ended up with our Pythagorean identities that are just equal to 1. And then from there, we realized that what resulted were just those double angle formulas that gave us the left-hand side. Okay, that's it for this one.